Good morning, everyone, and thank you for joining us for today's presentation. My name is Jean-Pierre Picard, Product Marketing Manager at CM Labs, and with me on the line is Marc-Alexandre Vezina, Product Manager for Vortex Software Solution. We're here today to talk about optimizing simulation performance. So today's presentation is part of our Vortex University series of webinar. If you're not familiar with the concept, Vortex University is a monthly presentation in which we take a topic and we do a deep dive on it, and we look at typically more technical topics, the ones you won't see around product release. We look at a specific subject, like today's optimization. We spend a full hour looking at different tools available, different strategies to attain that objective, and some real-life examples. You can keep track of upcoming sessions at CMLab/Vortex University, but you can also go on our YouTube channel and see the previous sessions of Vortex University, some of which we'll refer today, as we're going to be touching on a lot of different tools that we provided 1 hour long sessions on. Today's presentation is going to be split into 4 sections. We're going to start by looking at the different tools that are available to measure the performance of your simulation and analyze where that performance comes from, where there's slowdowns, where it's running efficient. Then we'll talk about some general best practices for real-time simulation. We're going to look at the dynamics, graphics, scene-level considerations, and these will be general strategies that we recommend you apply to every single project. Obviously, some will be more relevant depending on your application. For example, optimizing the dynamics will be very important if you're working on virtual prototyping, whereas graphics might not be as heavy and detailed in those applications. Then we'll look at 3 case studies where we ran into performance issues or performance changes that we weren't sure where they were coming from, and we'll look at how we tackled them specifically in the samples we have with Vortex Software Solution. And as usual, we'll finish today's presentation with a Q&A in which you can send us your questions and we'll answer them live. Now, if during the presentation you have questions or issues with audio or video, I invite you to use the right GoToWebinar interface and send us your questions. We've also made today's presentation available in PDF format on the right-hand side handout section. So don't hesitate to grab a copy, and if you have any questions after the webinar, you'll be able to refer to it and then email us. Those of you that are joining us that are not familiar about Vortex Software Solution, well, you've definitely chosen the right session because we're going into some very in-depth topics here. But kidding aside, Vortex Software Solutions is CM Labs' real-time visualization and simulation solution, and it's used for virtual prototyping, operator training, and operational planning. It contains all the tools you need to create simulation, and that includes mechanical modeling, object model import and optimization, scene creation, but it also includes obviously CM Labs' acclaimed dynamics engine, which provides you with very accurate multi-body dynamics and is augmented by our earth-moving, marine, and vehicle simulation modules and our cable module. And of course, Vortex Software Solution comes with an extensive SDK that allows you to integrate third-party system, be they software or hardware. So that gives you all the tools you need to create a complete simulation and simulator. Today's demos will include 2 applications. The first one is the Vortex Editor. We'll be spending most of our time in the Vortex Editor today. That's the desktop application that's used to create but also validate simulation content. And obviously, since we're going to be troubleshooting performance, then we're going to be doing that a lot in the Vortex Editor. But we're also going to show you how to use a Vortex Player to do those same tasks. Now, the Vortex Player is used to distribute simulation content. Typically, when your content is distributed using the Vortex Player, you're going to have a certain level of performance that you've attained, and you'll be really at the last steps of troubleshooting and optimization. All right, so let's jump into it, and let's look at the different tools available. Now, before we look at specific tools, I'd like to just refer again you guys to the Vortex documentation files. There's a lot of good content in there on simulation troubleshooting and optimization. There's a lot of best practices for collision detection, optimization of mesh and collision geometries, and constraints. We're going to be presenting a handful of those in our best practices, and they're all taken from the Vortex documentation where you can go into more details in a text format. And there's also obviously an overview of the different tools and the different properties you can activate in them. Right. So if we look at all the troubleshooting and optimization tools available in the Vortex editor, there's quite a few. There's the wireframe display, the inspector panel, and the debug display, and then there's a graphic statistics panel on the profiler. And in the Vortex player, you have two discrete tools, the graphic statistics panel and the debugger. Now, last month, we did the first part of our troubleshooting webinar series, and we looked at the wireframe display, the inspector panel, and the debug display, because those were really about troubleshooting unexpected behavior. This month, we're going to be focusing on the graphic statistics panel and the profiler, which are really used for optimizing the performance. All right, so let's start by looking at the graphic statistics panel. This is accessed by pressing F3 either in the editor or in the player. And what it does, it allows you to cycle between different information panels. The structure will remain the same. You're going to have your different measures on the left, and then on the right you'll have the current value, and then the minimum, maximum, and average values obtained throughout the current simulation run. So you'll be able to see the slowest frame rate that you've had throughout the simulation, and also the fastest, and the average. Obviously, the average is something that that is very easy to comprehend, but then the difference between your minimum and maximum will also tell you the gap between best performance in your simulation and lowest performance. And if there is a big gap, then you're going to want to look at when that gap occurs and try to figure out how to optimize that. So if we look at the first panel we have here, you start with the frame rate at the top. So we can see that our simulation is currently running at 27 frames per second, which is obviously not ideal, as we recommend 60 frames per second. But this was taken on a laptop system with a fairly sizable simulation. If you look under it, then you have different simulation components and the time they take in milliseconds to be processed. So you have the graphics update, and then you have the CPU draw and GPU draw. These in a vacuum aren't really that useful. What you want to do is compare those values with what you had before you made some changes and what you'll have after you make other changes. If you press F3 again, you're going to get to the second information panel, which shows you the details of your graphics content. So the number of passes it took to render the scene, and the content, the lights, the render bins, the vertex counts, all of these things. And again, these are useful as a comparison point with previous profiling, because you're going to be looking at the frame rate you're achieving, and you're going to be comparing those numbers with what you had before your changes. And finally, the last panel will show you the details of passes. So you can see here we have 38 lines. Now, that is the 38 passes we had here, and it's the different content of those passes and their time and frequency. So you'll have the time in milliseconds and the frequency of over 60 frames that they are calculated. The second tool is the simulation profiler. The simulation profiler is a tool that's used to show you real-time information about the different resources that the simulation is using. Now, just like the graphic statistics panel, activating the profiler will have an impact on performance. So because you're calculating things in real time and you're tracking them, this will actually impact performance a bit. So you have to take those numbers with a grain of salt, and that is, they are somewhat slowing down your simulation, and you'll get slightly better performance once you run the final thing. But this again allows you to compare the different events and how much time they take as part of your simulation process. So the profiler displays on the left the name of the event, and you can select and filter those events to see exactly what you want to focus on. Then you have a section on the time consumed by that event, and you have it in milliseconds. You also have it as a percentage of a time step and a bar chart showing you the relative value, and this is great to see where you're really spending a lot of time. And then on the right, you have a sequence that shows you, in a Gantt chart format, the different steps in a sequence and how long they take. So again, this gives you a very visual representation of how your simulation is being processed and rendered. So when to use a profiler? Well, this one's easy. You should be using it every time you're making changes to your simulation. So when you're adding or integrating new content, when you're changing values, you want to see the impact on performance. The longer you wait, the more elements you have changed, the harder it will be to compare with previous profilings. So that means it's actually useful as well for multiple types of roles. For example, if you're a graphics designer, you're going to want to profile your simulation when you're creating or modifying a graphic gallery, because that's going to impact the number of visual elements in your simulations quite importantly. And then this way you're going to be able to pinpoint when you have changes in your performance. As a mechanical engineer, you want to profile every time you add new functionalities to a mechanism. So if you're modifying constraints, adding different scripts, you're going to want to make sure that the performance remains at the levels you're expecting. If you're a level designer, every time you add new content or scripts to a scene, then you want to profile again and see how that impacted performance and if there's an option there to optimize it. If you're the system integrator, technically you're at the end of the process and the content you're getting delivered on the graphics, mechanical engineering, and level design side should have been optimized. But obviously you're going to be integrating the actual hardware if you simulate in there. So every time you are facing performance issues, you're going to want to test the performance to see where that issue came from. And sometimes it's going to be related to the way scripts are made, and then you'll have to go back to your colleagues and make sure that this is optimized with the simulator hardware in mind. So to activate a profiler, you can activate it in the editor and in the player. Then you need to go first into View, Windows, and Profiler, and it will add a panel at the bottom of your screen. You can undock it and put it on a second screen and get a better view of what's happening. In the Vortex player, you have a separate tab that is called Profiler. Now, one thing that's important is you must first enable the tree to be able to profile. And when you click on Enable Tree, then you'll be able to expand the different events group to see their profiling. Now, you can also filter results, and that's really useful because there are quite a lot of different events that are being tracked in the profiler, and some of them will have more impact on simulation performance than others. So the useful filters that you see here are the ones you'll typically see taking a lot of processing resources and time. That's where you have the biggest likelihood of impacting performance positively. So you can filter these, select the one you want to profile and the ones you want to ignore for now. Now, the profiler provides you real-time information. As I mentioned, it does have somewhat of an impact on simulation performance, so you have to take that with a grain of salt, but it will provide you the current value in real time. Sometimes you're going to want to be able to drill down and see exactly when performance dipped. And that's where the CSV exporter is really useful. You can capture all the data from your profiler in a detailed CSV file that allows you to look at each time steps and the cost of each event over those time steps. That's going to tell you, okay, you know, I have a very high processing time for such and such event at this point in time. What was happening, and how can I improve that? So I'm going to pass the controls over to Marc-Alexandre, who's going to show us those tools in action. Marc-Alexandre, it's all yours.
Thank you, GP. So what I've got here is the excavator sample from Vortex. So it's a fairly simple scene as far as simulation go. The main thing is that it's got several mechanisms and an earthwork zone here and a sky dome, all of which consume computing power. So to see what the frame rate is, I'm going to press F3 on my keyboard. And then I've got up here in the upper left corner, I've got my frame rate. So currently it's running about 50-ish, but it's hard to read because it's always changing, obviously. So I go over to the right and I look at my min, my max, and my average over the last 60 frame. And I see that I'm averaging about 54 frame per second, which is not bad. I'm dipping at 30, but that can change depending on where I'm looking and what's happening on the screen. So if we go up like this, you see that the time is changing a bit. If I press F3 again, I'm getting a slightly more information. So now I've got my graphic update time in milliseconds. I've got my CPU draw, and I've got my GPU draw. So right now, it's not too bad. The simulation is not active, so we're not seeing a lot of activity on that side. If I press F3 again, I get the same panel, only this time with even more information. Some of this will make sense mostly to a developer or a graphics programmer, but it's still useful to have. If we go to the next panel, here we have our breakdown of graphical elements. So it took 48 passes to render a single frame. I've got phase light in the scene. I'm dividing the render in bins, so about an average of 61 bin. I've got quite a few vertex, quite a few triangle in the scene, so I've got a total of almost 600,000 triangle in this scene alone, which is not bad. And you might be wondering where the lights are, since we don't see headlights on the vehicle or stuff like that. Well, the lights from the sky dome, they all count. So we have an ambient light, we have directional light, and you can see them here in the sky. You can see the accessories. So these lights count in your frame rate. That's why the sky dome is so costly, is that it casts shadow and it adds lights to your scene. If I press F3 again, then I get a summary of all the passes in my scene. So the directional light, the shadows, if you go through and you scroll a bit, you've got quite a few. Here at the bottom, I've got 4 passes for the mirror alone. And the mirror is just a tiny mirror on the excavator. So something that's important to remember, mirrors are expensive, monitors are expensive. Anything that renders the scene again is expensive. So use them sparingly and only when you really need them. If you press F3 again, the whole thing goes away. Let's take a look at the profiler now. So we go into view up here in the main toolbar, scroll down to window, and we've got the inspector, material table, and the profiler. Remember that last session we took a look at the inspector, which gave us statistics about the content of the scene. This time we're going to enable the profiler, and the profiler ends up being a new window at the bottom of the screen. And what it does, and I'm going to update it, refresh the information. What it does is that it shows us what where the computing power is going. So if I start my simulation, and one thing to keep in mind when you're using the profiler is that in itself it takes computing power, and the editor as a whole takes computing power. So what you're going to see as far as data here is not entirely accurate. It's more of a guide to help you optimize your simulation. So what we can see here is that most of the activity is taking place during the module update phase and the post-update phase, but we don't really have any detail about what's going on. So we go back into setting, and I go into my update, and then I say, okay, well, show me what's going on with the dynamic, show me what's going on with the earthwork. I've got humans in my scene. I don't have, oh, I've got graphics, of course. I'm not using a space navigator, metrics, audio, so I'm not going to use them. So I go update, refresh the data. Okay. Now I've got a little triangle shape that I can press, and this time I get more information about what's going on in my scene. So you can see that the dynamic engine is working. The graphic is taking up most of our time, so basically all the shadows and all these trees are eating up our rendering time. And earthwork is not actually doing a lot of work. So maybe if we dig a little, and we're going to see if, and you can see that earthwork is taking up slightly more time as I dig with the excavator, but not all that much. So that's good news. It means that our earthwork zone has been well set up. Now, we're going to close up the editor, and the reason I'm doing this is you don't want to have false reading by having 2 simulators open at the same time. So I just opened up the Vortex player, and the Vortex player is going to have better, more accurate statistics because it doesn't have the overhead of the editor. It doesn't have all the tools to create the simulation. What you want to do is, and I'm going to load up my scene here, whenever you're building a simulation, you have to test it on the final hardware. You can't rely on the information in the editor because it's not going to be accurate. You're going to get false reading. You're going to have the overhead from the editor itself. You're going to have, you're going to be running it on a single desktop computer. If the final simulation is intended to run on a multi-computer setup with multi-screen, you really have to test the performance on the final hardware. Only then will you get the real number for the performance. But using these tools, it's still useful. So now I've got my scene opened up here and it's running. So if I go into my main viewport and I press F3, again, I get my frame rate, and you can see that it's slightly better than the editor by 2 or 3 frames. And then I can again press F3 to get more information. Again, more information. The content of the scene. So this time you'll see that we have only 3 lights compared to the 5 lights previously. You say, we didn't remove any lights. Well, that's because we have 3 lights in the sky dome. We've got our ambient, we've got our sun, and we've got our moon. And the 2 lights that are missing are the default light that the editor put in case you don't have any illumination in your scene. Remember what I said about the overhead from the editor? That's what I meant. So press this again, and then we come back to our scene. Now, if you go into your control panel, up here in the tabs, there's one called the profiler up here, and the profiler is not running right now. We don't want it running all the time because it's going to consume computing power, and that's bad. It's computing power that's not available for the simulation. So I'm going to enable the tree, and in my section timing, now I've got my time in millisecond, the sum total it took, and the description of what the task is. So now I've got everything listed here. I can close this down or reactivate it as I need. And there's also a section at the bottom called values that gives you additional information like the cycle time, the memory consumed, and so on. So I'm going to deactivate it because I don't need it. Another interesting thing that you've got here is a button for graph here. So what it does is that it creates a graph, and then you can go back here in your panel and say, okay, I want to see my dynamic engine. So I right-click on the time, show dynamic time, and now it's showing me the dynamic engine during the simulation. So you can see that it's oscillating because it's checking what's happening. If I take the earthwork system, I can also put it in my graphic. So the earthwork system is not really visible because it's right here at the bottom. Remember how much a little time it took compared to the dynamic and graphic update. Now, once this is done, I've got a profiler capture up here that I can do start capture, and it's start capturing information, telling you how much time has been spent on it. Stop the capture, and then I can use these to go select a folder and then save the information. The filtering that GP was talking about is right here, so we can check the filtering settings. So right now we've got disabled category, content, and dynamic. We can swap stuff here. For example, I've got no marine in my scene, so I'm going to drop marine there. I've removed the audio. I put it in a disabled category, and then they're going to disappear from the list. So it's going to take even more. It's going to take less time to do the profiling update. Finally, here, advanced modes give you additional information, and stop on pause means that if you pause the simulation, the profiler has stopped as well. If you don't activate this checkbox, the profiler will keep going even though the simulation is paused, so you might not see all the data that you really want to see. Back to you, GP.
Thank you, Marc-Alexandre. So now that we know how the tools work, we're going to look at a few general best practices that will help make sure we have good performance on our simulations. So let's start with graphics because they have a very big impact on simulation performance. As we've seen just right now, graphics are one of the most costly steps of the simulation rendering process. So the first and most obvious rule is to limit the number of triangle end nodes. Now this might sound like something that's really obvious, but sometimes there are some big gains that can be achieved with some minimal level of effort. Good example here, and we'll come back as to how this is achieved in our case studies later, is a crane model that we've imported that had a lot of graphic nodes, a lot of triangles. Now, our model started without textures at a cost memory of 4.5 megabytes. We actually were able to achieve a 50% reduction on the cost of memory by simplifying the model. So you can see the number of separate nodes that disappear. You have less draw calls, you have less triangles, less vertices, and this provides you with measurable gains in performance. The second one is a bit more subtle. The second best practice is to use textures with appropriate resolutions. So what we're showing here is a hook model for a crane that we were working on. There's a lot of very nice details on this hook. You can see there's scratches, there's layers to simulate depth on the markings, there's some rust on it. This all looks very great, and seen from this close, definitely, you know, this is a very nice texture. But the reality of it is, once you're going to be in the simulation, this hook will be located at a certain distance that you will not be able to see any of these details. So by using this resolution, which is 4K resolution, then you're going to be spending a lot of resources rendering a very small item that will not have a measurable impact on the engagement of your simulation. So you could replace this with a much simpler texture that would have only 1 layer, 2 layers on it, lower resolution, and you would not see a decrease in realism. Another thing to consider is which meshes can you instance and which textures can you instance. And as an example, we're going to look at the Abraham tank here. So you can see on the different wheels, you know, we have 7 wheels. All of these, and that's the same on the other side, all of these use the same mesh and the same texture. So you could instance those and limit the number of draw calls. So you could have all 7 on one side or use the same mesh and the same texture. So you're going to get, again, some gains in efficiency. There might not be that big of a gain just for instancing those wheels, but there's actually quite a few elements you're going to be reusing in a typical simulation. And if you do it on every objects and every meshes you can instance, then it's going to add up. And finally, definitely use level of details. This is a short video we've created that's part of our 6.8 launch webinar, which you can see on our YouTube. The level of details features allows you to defeature a model as you are gradually further away from it. This is obviously a very exaggerated example because we see the transition, but normally you would set it so that once the boat is far enough away from your participants, then you defeature it without them being able to even see it. Now that's going to mean you're going to be able to replace a lot of models that are not part of the current point of focus by lower level of detailed models and textures, and you're going to spend your processing power on elements that are part of the current action of the simulation. If we go on the dynamic side, a good potential strategy is to merge parts that move together. So you can see here that we've got a separate part for the turret, and then we've got our assembly for the chassis. Now, if you're doing a scenario where you're going to be moving that turret around, then you definitely want a part that is separate from the chassis. But if you're doing only a driver simulator, then you could merge that part to the chassis without affecting the functionalities of your simulation. And you'll, again, be improving performance. You're reducing draw calls, you're making everything simpler. Now for this next one, I'm going to have Marc-Alexandre explain this a bit to you, why you want to use primitive collision geometries as much as possible. Marc-Alexandre.
Thank you, GP. So whenever possible, use primitive collision geometry, because calculating the collision between a box and a sphere is a lot simpler than calculating the collision between convex or even triangle mesh. And what we see here is the forwarder model from the sample, the Vortex sample. And the rear deck is composed of arms and that hold the logs together. Now, the entire rear deck is one graphical node, and a lazy designer, and I'm guilty of this when I first created the model, will just grab the node and attempt to use the automated tool to create one big convex mesh that's going to make it, that's going to give it a collision geometry. But when you do that, and then you open up your part, you see that there are several hundreds of little parts that the computer attempted to fit to exactly match all the curves inside that graphic node. All the arms on the rear deck, the slope is exactly there. You don't need all that. It's going to slow down your simulation to a crawl. So I deleted the convex and I started over doing the work manually. So the bottom of the rear chassis, it's a box. The little support arm for the poles are curved. Well, they're made out of boxes as well. It's just that Each box is slightly oriented to approximate the curve. Even though it's not a perfect match for the graphic model, it doesn't matter. It's still a slope, and the log will roll down just as it would in real life. And that means instead of having several hundreds of collision geometry composing my rear chassis, instead I ended up with maybe a few dozen. And that sped up the simulation considerably.
Great. So our next best practice is to make sure you don't over-constrain your mechanism. And for this, we're going to look at a grabber model. Now, if you look at the real-world part, you would have 8 different constraints on this grabber part. Marc-Alexandre, can you explain to us how you can simplify this in a simulation?
Absolutely. So as GP showed, there's the real thing as 8 hinges in order to keep the jaws parallel when they open and close. Now, if we want to simulate this, the first obvious idea says, well, I'm going to put 8 hinges. And this is a bad thing because it over-constrains the system. It creates loops. It creates, it forces the computer to calculate paths to send the energy somewhere. And it's really bad. If you want the whole technical explanation, you can find it in the documentation along with the equation. So I'm not going to go into that, but you need to give some free play in your mechanism for it to absorb the excess energy. For example, torsions and lateral motion. So in this case, we don't want to use 8 hinges. So we're going to try and do something else. We're going to just use 2 hinges and 2 ball and socket. So the ball and socket are going to allow it to twist on the side, and that's going to be give the computer some path to put the energy into. Keep in mind, even though it's a ball and socket, you can still force it to move in a certain way. So it's not actually, it's still going to actually move as an hinge. But there's an even better way to do it, and then is that by using angular tree constraint, which means that the computer is going to be able to move it in torsion and sideways, and if you have energy or forces coming that way, they're gonna have somewhere to go. There's going to be some give to the to each hinge on the side and in torsion, so that way the simulation is going to be a lot more stable. So I invite you to look at the technical section, the technical notes in the Vortex documentation, to take a look at the whole explanation with the equation. And we have a 21 constraint available in Vortex, so make sure you pick the right one to keep your simulation stable.
Thank you. Now, other considerations for the dynamics are related to very specific use case. For example, if you're working with an earthwork zone. If you're working with an earthwork zone, you'll be familiar that you can customize the grid size. But how do you define the appropriate grid size? Because obviously, if you have a smaller bucket, such as the one seen on an excavator, you're going to have a grid size that's going to need to be more precise than if you have a larger bucket, like the one on a wheel loader. What we recommend is to use a grid size 1/10 the size of your moving tool, and start from there, and then see what your performance looks like, and then you can play a bit with it to achieve the performance and accuracy balance that you want. But obviously, if we had a grid size that was as precise as the excavator on the wheel loader, we'd be basically wasting a lot of resources maintaining something that will not show in actual simulation accuracy because we have a much larger bucket. If you're using cable, definitely pay attention to when you can use adaptive cable technology. If you look at our ROV simulation portion of the offshore sample, at the bottom of the ocean, which is 600 meters down, you have an ROV that is tethered to the ship by a very, very long cable. This cable will not come into contact with any object because it is simply in the water. If you don't use adaptive cable technology, every time step you're going to be looking for potential collisions with that cable. If you use adaptive cable technology, then the simulation will dynamically adjust the refresh rate of the cable based on its proximity to other objects. So some segments will be updated less often because there is no chance of collision with other objects. And that's going to free up important resources to use elsewhere in your simulation. You also want to make sure you limit the segment length of flexible cable to a reasonable precision. If you look at the mobile crane sample here, you can see that we have a segment length for our spreader that is set to roughly repeat itself about 15 times. Now, if we wanted to be even more precise in the way the cable moves, we could have increased it to double the frequency, so you'd have a shorter segment length, but that's going to take a lot of resources. And because we're going to have it under tension for the majority of the simulation, it would be wasted because this will be almost behaving like a rigid cable. Now at the scene level, Marc-Alexandre touched on this point earlier, the Sky Dome is fairly resource intensive. So if you don't need time of day, then consider using a skybox. A good example of this is an indoor simulation scenario, like the forklift simulator that we have in the sample. Now you can see that we have some windows with outside light coming in. But because we're only getting light from the outside shown in an indoor environment, we don't need to have a precise position of the sun. We don't need to be able to select a precise time of day. So what we use is we use the skybox, and we saved a lot of resources by having a much more efficient solution that doesn't again affect simulation accuracy. Also pay special attention to shadows. Shadows are very cost intensive, so you have to tune them to achieve the result you want. And you can see here the difference between very precise shadows and very loose shadows. Depending on your available resources and the distance between the shadows of your scene and your operator, consider tuning it somewhere in between to achieve the performance you need. Again, getting a good frame rate will do more for the engagement of the operator than having nice crisp shadows. The next one will be the subject of one of our case studies in a few minutes, so I'm just going to go over real briefly, but consider using light maps in scenes with a lot of lights. And you can see here our EOD scene, which has a lot of lampposts. And if you look up from the top, you can see that there's actually quite a lot of lights. Now, in a few minutes, Marc-Alexandre will show us exactly what the impact of performance of this is. But what we did to simplify it is use a texture that defines light points. So we'll look exactly how to set this up in a few minutes, but this is one that has a very important impact on performance. For scenes, also consider using Vortex configuration to remove unused objects. Now, if you're not familiar with the Vortex configurations, I again invite you to look at our Vortex 6.8 launch webinar on our YouTube channel. But Vortex configurations, in a nutshell, are a new feature that allows you to turn on and off different elements of a simulation. They can be at the mechanism or scene levels. In this case, we are activating and deactivating attachment for our ROV. So if we activate them, then we're going to see them and render them and calculate their collisions as well in the scene. But if you don't need the arms, then you could deactivate them and save resources on those. Now you can go further and deactivate the entire mechanism in a scene, and that's going to have a significant impact. Now this next one, as with regards to particle effects, such as the bow wake here on the ship. Marc-Alexandre, maybe you can explain a bit how you've made sure that this was an efficient strategy for the particle effect.
So when people think about particle effects, they often think about little spots of light and material just hanging in the air and being projected, and just like fireworks, for example. In reality, doing this would take an immense amount of computing power. So what we're doing instead is that we're replacing each of the little spots of light by a little square that has a texture painted on it. And in this case, the texture looks something like this. So it's a splash of water surrounded by an alpha section. So basically everything that's black is going to be transparent to the computer. So whenever a particle is generated, instead of being just a simple point of light or a pixel, the computer is going to place that graphic inside the simulation and then move it as the particle goes. And we're using something similar in the earthwork system to show you the dust and the chunk of material that are falling out of the ground. So if you go look into the scene, it's in the offshore scene sample for 6.8, you'll be able to see the graphic material for the splash, and obviously you can modify it. You can use different texture if you don't like the aspect. You can change the color if you're using navigating through different waters. So if you want to adjust it to be a little more green or blue or to fit your scene better, you can do it. And you can also do the same thing for non-maritime application, for example. If you have a vehicle that's going through thick dust and it's throwing up huge plumes of dust, you're going to be able to put something like this, but in a beige color, to give it volume without having to have a huge number of particles, because the more particle you have, the more computing power you're going to have to devote to it. If you're doing smoke, for example, instead of having lots of little black pixel going up, do a sort of smoke cloud in 2D and just put that as a particle and look at your smoke cloud going up. Is going to be a lot more realistic without consuming all the power of your computer.
All right, and then if we look at specific extensions that you can tune and modify to affect performance. So the first one is selecting the right anti-aliasing method. So there's 3 anti-aliasing methods available in Vortex software solution. Well, there's 2 of them, and then there's the not using anti-aliasing. So you can see that depending on your scene, you could have some jagged edges on your lines. So you could consider using either FXA or SMA methods. Now, FXA will be more efficient in terms of processing power than SMA, but it will have a slightly fuzzier look. Again, adapt this to the hardware you have available and the resources you have to dedicate to anti-aliasing. This can have a very material impact on performance. And Marc-Alexandre referred to this earlier when he was talking about the excavator model. Consider limiting mirror reflection quality and frequency. This little mirror here is actually considered an extra viewport, so you have to render the scene an extra time every time you add a mirror. Now, if it's useful because your operator must learn to operate it, obviously you're going to want to use it, but make sure that you fine-tune the quality and the frequency appropriately. So that closes the chapter on best practices. Now we're going to look at how we applied them to fix 3 different case studies where we had performance challenges. The first one is the EOD sample that I've shown really briefly a moment ago. We're going to look at what issues came about when we switched the scene to a nighttime scene. Specific challenges included the high number of light sources, the sky dome, and the tether on the EOD. So Marc-Alexandre, I'm going to hand over the controls to you for a quick overview of the sample.
Thank you, GP. So what I've done here is that I've opened up the EOD scene and I made a little change to show you the impact of the on the performance. So as you can see, there is an accessory for a spotlight over each lamp in the street. And then when I start my simulation, these lamps will create a spot of light under each lamp like you would expect. And you're saying, well, yeah, that's exactly like I would do it. If I hit F3, so I need to click in my viewport. If I hit F3, you can see that my frame rate is very, very low. And this is bad. This is almost unusable. So 12 frames per second, it's going to have a lag. The operator is not going to be able to use it. So we really need to improve this. What we're going to do is that instead of using a separate light for each of the pole, so I'm going to remove these from the scene, we're only going to use the spot for the poles that are really closest to the action, like this one, so that we can have shadows in real time if the robot goes underneath. And instead, what we're going to do is that we're going to use a street map. So what street map looks like is this. So it might look weird, but this is actually a mask that we're going to put in front of a single spot that's high above the scene. So we've used a directional light here, and we've put it really high above the scene, and then we've got in the parameter the projected texture. So what we did is that we went into a top view of the scene, we took a screen grab, and then using a computer program for graphics, we went and we painted holes wherever there's a spotlight. And what it does is that once you've activated, it only shines the light where there's a hole in the mask, and the mask corresponds to the pole. So we get the same effect, but instead of having 12 light in the scene, now we have only one. And we can see that our frame rate jumped to 20 right away instead of 12. So it's a major improvement. Other improvements, see, it went up to 24 and it's slowly climbing. Other improvement, the sky dome. We have a sky dome in place. We could, if we wanted to really optimize the scene, change it to a skybox, because the sky dome is not bringing a lot to the lighting of the scene. We have a moonlight, so the moon is not enabled here. So we're not even using the moon. So there's really little point in having the sky dome in the scene. So if I delete it completely, you see that there's not a lot of difference in the sky, but we're seeing a small improvement in the frame rate. So we're going to refresh it. Another thing that you want to do in the PackBot tether, so we created a tether here. So the tether is right now is in gray because its configuration is not active. So I'm going to activate it to bring it back. So you've got your generic cable. It's important when you set up your flexible cable that you give it proper definition. So we've put some damping to keep it stable. It's hooked to the robot in the truck. And in the segment definition, so we've got our flexible part of the thing. We've got a preferred section length of 20 centimeter. Why 20 centimeter? Because this is going to be a fairly close-in simulation, so we really want to have a good flexibility to the cable. We don't want to have weird sticks effect going on. So you can see that the cable is at the back of the truck here, and my frame rate drops while I'm active, and that's entirely normal. Now, if I was running this scene through the player, you would go back to nearly 60 frames per second. So you can see that the cable here is adaptive, and what this does is that it's going to freeze the section of cable that is not moving. So as my robot is moving away from the truck, this section up here is not moving. So the computer is merging the various segments together and stop caring about what they collide with and whether they're going to move. And I've put an active joint budget of only 10%. So at any time, only 10% of the joints are active. So it creates a cable that's not very demanding in terms of simulation.
Thank you, Marc-Alexandre. So we're going to move on to our sample case study. This one we're going to take a look at the impact of the grid size on for earth moving zone on simulation performance. We're going to do this in the excavator sample, but this is the kind of scenario we face every time that we build a new earth moving simulator as part of CM Lab's construction training modules line. So Marc-Alexandre, I'm going to let you open up the scene and back the controls to you.
Thank you, GP. So I've opened up the excavator again, and what I want to show you this time is the effect that playing with the earthwork system has on the scene. So right now I'm running at about 56 FPS, which is pretty good. If I was running this in the player or on a simulator, I would get a solid 60 frames per second, which is what we're actually aiming for. So if we look in the earthwork zone, in the dynamic, we've got the dimension of the zone and we've got the cell size. Now these are two parameters that are important to get right because they're both costly in terms of simulation. So if you look at the cell size, usually what you want to do is that you take your tool here, the width of the tool, and you divide it by about 10 to give an idea of the cell size that you're going to use. If you use too small a cell size, Like in this case, I'm using a 3 centimeter cell size, and then I launch my simulation. The whole thing is going to just collapse because there's going to be too many cells in the scene. So it's terrible. So that's completely unusable. So you want to make sure that you choose a cell size that provides you with accuracy, but which is also decent for the frame rate. You also want to make sure that your earthwork zone is only as large as you need it, because the height field needs to be kept in memory. And the more cells you have in there, the larger it is, the more memory it's going to take, the more computing power it's going to take to check for deformation and changes in the height. So really, please only use the earthwork zone from the size that you need and the depth that you need as well. So in this case, if the excavator is not able to dig further than a few meters, there's no point in putting an earthwork zone that's going all the way down to China. Back to you, GP.
Thank you, Marc-Alexandre. All right, so moving on to our third and final case study. This one is going to focus on graphic gallery optimization. We're going to look at the crane model that I brought up earlier, and we're going to see the difference directly in the editor between the graphic gallery before and after optimization. This is using the CAD Optimizer add-on tool, which is available as an optional add-on for Vortex software solution. And if you're curious about exactly what you can do with the CAD Optimizer add-on, I invite you to look at our YouTube channel at previous Vortex University webinar from last spring, where we did a deep dive into this exact model and how to optimize it. So Marc-Alexandre, back to you.
Thank you, GP. So I've opened up the graphic gallery with my CAD model. So the CAD model has been imported with this button here. And then I'm going to use the colorize node button to show you how many nodes it has. So you can see that everything is broken down into tiny segments. And if we want to view Windows Inspector, so we're going to have the Inspector window. Okay, it's hidden. So if we choose the gallery here, we see that we're taking up almost 5 megs of memory, and there's 874 graphic nodes in the entire model. So that's quite a few draw call, and it's going to stop your simulation to a crawl. And also making the parts is going to be a nightmare because you have so many nodes to deal with. So I'm not going to go through the whole process because we devoted a whole webinar on this previously. I just wanted to show you the inspector, the difference between the two. So now our number of graphic node is only 43, so it's a massive improvement on the previous model. And this is also going to be making the parts creation a lot simpler, because the boom is one part, so now it's just one graphic node. So it's a lot more efficient than just trying to have this huge hierarchy of little nodes trying to move together. Back to you, GP.
Thank you, Marc-Alexandre. All right, so we're going to move on to the Q&A in a minute. Just before we close, I just want to come back on one of the big conclusion, the key takeaways from today's webinar. Profiling simulation performance is something that's best done early and often, because what you want to do is you want to be able to compare performance before and after major changes. Profiling is something that cannot really be used in a vacuum because you're targeting obviously a certain frame rate, but exactly where you can go to optimize performance and where you have a budget to make those improvements, something that you'll see only by being able to look at historic data. Now, I invite you to send us your questions using the right-hand side questions box on the GoToWebinar interface. For those of you that will be leaving us, thank you again for joining us for today's webinar. We hope to see you next month on early December for our next Vortex University webinar. This one's going to be a bit different. We're going to do a big deep dive on a new sample we are working on for a military environment. Those of you that will be visiting ITSEC will be interested to know that you'll be able to see it in action over there. So we're going to go from the start to the finish of this simulation, and we're going to look at how we optimize graphic, the different strategies we took to create an interesting scene, the integration challenges, all of these will be a very interesting look at the simulation creation and optimization process. So you can look at the cmlabs.com/Vortex University for more information. It'll be on December 13th at 9 a.m. EST. So thank you again for joining us today. As usual, look to your inbox for a copy of today's presentation as the video will be uploaded on YouTube in a very short order.